There's a reason we have this order of draw. The reason is because of the additives that are in these vacuum tubes. Okay, so my yellow, which I don't have here on this table, red, light blue, these things that's inside of them that gives the blood its properties for whatever sample state that we want to test will interact with each other if one is mixed with the other. So if we do one first, okay, then we don't have to worry about this one interacting with this one if it comes after. If we did it first, there would be a problem. There would be error results or the samples would be tainted. So we have to make sure we do some after others. Okay, and then also each of these tubes stand for different types of tests. We're going to review that today. And I think I'm going to start right here on page 127, and then I will go back and cover the previous part of this chapter on Thursday. We'll finish this chapter up. Just because it's so crucial, and I got everybody here. So starting at the bottom of page 126, it says the types of blood specimens. Can anybody tell me what those are, just right offhand, other than Marissa? Actually, Marissa, go ahead and tell me. Plasma. How do we get these three? How do we separate blood into one of these three components to test it, right? Whole blood is blood collected, I'm reading the top of 127, and mixed with an anticoagulant so that will not clot. Okay? So I'm going to go ahead and put that right there. Anticoagulant. Hannah, what does that mean to be against coagulating, anticoagulant? It's not going to clot. In other words, your blood is going to stay in the whole form, just like it came out of your arm into the tube. It's going to stay just like that because there's a chemical in there that's going to keep that blood from activating clot factors and stuff like that. This is good for when we do test any hematology test, like cell counts, complete blood counts. I'm going to put shapes here, but the real word is morphology. Okay, are those cells being produced correctly? Are they sick, like they have sickle cell shape or something? We want to make sure they're formed correctly. If you want to look at any hormones in your blood, the paragraph also states, well, that's pretty much it. Metals. So we might have to worry about lead poisoning, or we want to make sure you got a certain metal like magnesium or iron. We need whole blood for that. Okay. There are three types of whole blood, this is one part that you all are in the dark about. Marissa was here for. We've got venous blood, arterial blood, and capillary blood. Three types, okay? Tell me a little bit about something about venous blood, Marissa. It's in my veins, first of all, right? Not my arteries. What's one characteristic of this blood? We color our veins blue or red? Blue. Veins have blood that is low in oxygen. That's the only place in the body where it is like that because it's within the pulmonary circuit. Everywhere else in the body where we're drawing blood, you can kind of put that to the side now and think about blood you're drawing out of people at this point. And if I draw blood out of your vein, that vein is on its way back to the heart for that blood to be cleaned and circulated back throughout your body. You call pulmonary veins red because it's still technically draining towards the heart. It's still a vein, but it happens to be coming from the lungs and it's oxygenated. it's flip-flopped in this one area. And then the arteries are also flip-flopped in that one area because they're carrying blood from the heart to the lungs, but it's blood that's on its way to be cleaned. That's the only place you have to worry about that. And you can almost kind of forget it at this point, because now we're talking about blood we draw to people from here on out in the course. All right, so this is low in oxygen. It's typically considered blue in our books and in our diagrams. And when we look at blood in your veins, you can see your veins are sort of blue. That's because light is reflecting off of that blood. Okay, it's low in oxygen, and that's just the color it gives us. We turn blue when we lose oxygen, right? When we lose our breath, same thing, okay? So low in O2. Arterial blood, on the other hand, is bright red. It's in our arteries, and it's under a lot of pressure. Think of the place you can feel your radial pulse. That's the radial artery. It's strong enough where you can actually palpate it when you squish it up against the bone. You can't do that with veins. Pressure's not high enough. Okay. High in oxygen, other arterial gases we can measure here. We'll talk about one time we may draw from arterial blood. It's rare for a phlebotomist, but it's special training, but it's a possibility. Later in the chapter 13, I think. And then capillary blood is right in the middle. It does resemble arterial blood a little bit more, but capillary blood is between clean and dirty. It's where the exchange with the cells takes place in terms of gas, nutrients, whatever it is blood needs to do for cells. Okay. Capillary blood is what you would test from a finger, because that's not a vein or an artery. It's a capillary, microscopic, right? Okay. So you get why we need to keep blood whole. There's 3 types of that. The second form of this fluid we take out of our bodies, I'm going to rearrange this here real quick. Plasma. Plasma is the fluid portion of blood, including fibrinogen and other clotting factors. So I'm going to put that first thing. What's significant about clotting factors? They help us to do what? Clot. They help us keep our blood in our body, right? Can you give me one clotting factor? Do you know? Look, you might want to go back to chapter 7 and look at that clotting cascade. Things like fibrinogen and thrombin, they're going to be in plasma. Look at the bot right there. You were on it. Page 112. So quick things scan. Like prothrombin and fibrinogen. Save. If we separate plasma from whole blood, then these are still going to be here. Okay. And sometimes we want to make tests without that. So we have to take them out. And that leaves us with serum. And it is just plasma without clotting factors. This is a very important concept. I want to make sure you get. It's like one of the first things we ever talked about. Giving up on that. Okay. So how do we get clotting factors out of serum? That's what we're going to learn here in a minute. Okay, it's really got a lot to do with that composition of blood thing we're talking about. So these are the 3 things we can test. And you know how we've got some tubes that say serum, some tubes that say plasma, and the lavender tubes say whole blood on them. That's what we're talking about. Okay. So plasma, just reading here, number 2 on 127, is the fluid portion of blood, including fibrinogen and other clotting factors. Plasma is obtained by collecting whole blood in a tube containing anticoagulants that prevent clotting. The sample is then centrifuged and the plasma is aspirated or sucked out of the top of a little syringe or tube. Okay, plasma is used for coagulation studies. It is also used for short turnaround time stat chemistry tests where there is no time to wait for clotting to occur before we spin it down or centrifuge it. Okay? So if I want to know how you're clotting, I'm going to need this. I don't need all those other cells that we could look at here. I only need this stuff. All right. And this takes time for this to clot up and sink to the bottom where I would have serum afterwards. So if I don't have time for this to do a chemistry test, I can use this, even though it's not ideal. My machines like to have pure serum that's got none of that stuff in it. But that's what they're talking about. And so serum is the fluid portion of blood that remains after clotting. The clot traps cells, platelets, and clotting factors. No anticoagulant is used collecting a serum sample. So if everybody remembers, we've had a blood, or I've had a tube of blood before that we filled up with regular blood, and we let it set and clot. And after that was done, there was a yellow straw-colored fluid up here. And there was a dark red clump down here. Okay, this was all the cells and clotting factors where they had been activated and clotted and sank to the bottom. So if I take out clotting factors, what do I have left over? Serum. Okay, and once that's done, once we've given it 30 to 60 minutes to clot, then we can spin it down and separate any minute leftovers and get that sample really pure, and we can take it out and do our chemistry test or whatever else we want to do, right? Unlike plasma, serum does not contain fibrinogen or other clotting factors, which are left behind or used up in forming the clot, and thus cannot be used for routine coagulation studies. Complete clotting takes 30 to 60 minutes, depending on the presence of clot activators. During that time, the tube should remain in an upright position. Leaving the tube upright during clotting prevents adherence to the sides and the stopper. So if you take your tube after filling it out, you might invert it or whatever, and you just lay it down on the table like that, then the clot's going to form here. You don't have that nice column of separation where you can get your sample out. So they're saying, don't leave it like this, don't leave it like this. You want to leave it upright. So we got those purple things back there. When this occurs, residual cells in the clot can contaminate the serum, resulting in erroneous results. Once it's fully formed, the sample can be centrifuged or spun down to separate the serum from the clot. It's important to allow the clot to form fully, otherwise strands of fibrin in the serum will interfere with chemistry instruments, causing bad results. Okay, additives. Most blood collection tubes contain one or more additives. Additives include anticoagulants to prevent clotting, clot activators to promote it, and thixotropic gel to separate components. Don't be afraid of that word. It's just an inert looking snot stuff in the bottom of this. It's just like gelatin, nothing special about it. Any tube containing an additive must be inverted and mixed well immediately after removal from the adapter. Gently turning the tube over, then back again, that equals one inversion. So 1, 2 is what they're saying. You should never shake a tube because it will cause hemolysis. What's hemolysis, Hannah? Yes, very good. The exact number of inversions needed varies by the tube type, but most need 5 to 8. Okay, so I'm gonna erase this if everybody's good with it, and we're going to talk about the different additives that we can use to get one of these 3 samples. And we might have to go over this again. I don't know if I'll even get to most of it today.